Hi! In this video, you will learn about separation processes in states of emergence. First, let's talk about concentrations. A concentration is no more than the number of moles that you have in a specific volume. For instance, here we've got a tank. This contains three types of molecules. If you were to calculate its concentration of each specific molecule, you'll have to find the number of moles of that molecule and divide its quantity by the volume. Similarly, we have molar fraction. This is no more than the relationship between the number of moles of a substance divided by the number of moles of all the substances. More specifically, a mole is just some atoms. As here we see, it's 6.02 times 10 to the power of 23. So, a molar fraction is no more than knowing how many atoms of a substance we have per each amount of atoms of all the substances. And more importantly, if you calculate the molar fraction of each specific compound, its addition has to be 1 because that reflects the 100%. In this case, a chemical equilibrium is no more than when the reactants become the product and the product returns back to be the reactant. This is like playing.
Gas mixtures are composed of different gases, and their concentrations can be expressed in terms of mole or weight fractions. Each gas contributes to the total pressure, which is the sum of the partial pressure of the components. This equation shows how the total pressure of a gas mixture is the sum of the individual partial pressures. But what are the partial pressures? It is the pressure that particular gas would exert if it were alone in the total volume occupied by the mixture. Partial pressures and mole fractions are proportional. Why? Because both depend on the same number of moles of X component in a gas mixture related to the total. This is explained by the ideal gas law shown below. This law states that the pressure of a gas is directly proportional to its number of moles when the volume and temperature are constant. In this sense, the partial pressure is related to the mole fraction that measures the proportion of moles of a gas with respect to the same total of the compound. This means that a gas with a higher mole fraction will contribute to a higher partial pressure, which demonstrates its proportionality. According to Avogadro's law, at constant temperature and pressure, the volume of a gas is directly proportional to the number of moles. In the image, if we keep the same amount of gas, same molecules, but change the volume, we will be altering the conditions for Avogadro to be constant. In the first part of the image, normal volume, the space between the molecules is adequate to maintain a stable pressure. In the second part, by reducing the volume but keeping the amount of gas constant, the molecules are compressed into smaller space, which increases the pressure. This indirectly shows that if you wanted to restore the initial volume in this compressed condition, you will need to remove molecules to comply with Avogadro's law. Here you can see an example of how to calculate mole fraction and average molecular weight so that you can put your knowledge into practice using the formulas to find each answer.
I'm going to talk about what is gas liquid equilibrium. At the fifth point, I have a question. Did you know that molecules in one liquid can escape into the air, forming a gas? This is that generates something called vapor pressure. I'm going to talk about the second point. The second point is effect liquid composition and the temperature. The gas-liquid equilibrium depends on factors such as liquid composition and temperature. In mixture, each component generates a pressure proportional to its amount. This is explained by Raoult's law and the Henry's law. The latter tells us that the amount of gas dissolved in a liquid depends on its pressure and specific solubility constant. For example, carbon dioxide in a carbonated average, its bubbling occurs because the pressure decreases, releasing the gas that was dissolving.
What is solid-liquid equilibrium? When you mix something solid, like sugar, with water, the solid starts to dissolve because the water breaks it into tiny pieces. But there is a limit to how much the water can dissolve, called solubility. If you add too much sugar, the extra stays in the bottle and the mixture is saturated. So now, what happens with heat? Heating the water can dissolve more sugar because heat makes the water molecules move faster. That's why sugar dissolves quicker in hot water than in cold. If you cool it down, the extra sugar will come out on the solution and form crystals. First one is unsaturated. The solution can still dissolve non-solute like sugar and water. It is not full yet. Saturated. The solution has dissolved as much solute as it can in that temperature. Any extra solute will dissolve and will settle at the bottom. Supersaturated. The solution holds more solute than it normally can at that temperature, usually achieved by heating and then cooling it carefully.
What is equilibrium concentration relationship? Okay, imagine a process where we want to separate different compounds of a mixture. This process is based on a simple principle. Each compound prefers to be in one part of the mixture rather than another part. For example, in a mixture of oil and the water, the oil prefers to be on top and the water on the bottom. Well, we can also represent this preference of the components graphically. For example, a diagram is used to show the relationship between the amount compounds is one part of the mixture and amount in another part. For example, we have this diagram where we can observe this equilibrium curve. It represents the temperature at which the water and the oil phases begin to separate. Phases region between the molar fraction of the zero point 0.2 and the zero point 0.8, water and oil coexist two immiscible phases, and separation the points they indicate of the two phases regions. Why is it important? The concentration equilibrium relationships are useful tools for understanding and design process. For example, when brewing coffee, caffeine is transferred from the coffee grounds and the hot water. And another example is the distillation of petroleum. Different compounds of the petroleum, such as gasoline and the gasoline, are separated by taking advantage of their different boiling points.
In multi-state contact process, two strains, light and heavy, enter into contact flow to change components. Mass balance are used to determine flow rate and concentration to each stage. For the lighter strains, flow is denoted as the letter P, which concentration the letter G, while for the heavier strains, flow is letter L, with concentration is letter X. By applying mass and component balance, we derive an equation of the relate to concentration between states. In simplified case, where flow rate remain constant across state, the equation is this present in the legs. This equation is critical in the sync of optimizing process like distillation, ensuring efficient component transfers, and equilibrium.
The calculation of separation in contact equilibrium processes is a common method used in industries to remove unwanted components, like impurities from a material. This process works by bringing two phases, such as a liquid and a vapor, into contact. During this contact, the unwanted component moves from one phase to the other, making it easier to remove. To understand this better, we need to focus on two key principles. The first is the equilibrium relationship, which tells you and how the unwanted component is distributed between the two phases. In this example, the concentration of the impurity in the vapor G is 10 times the concentration in the cream X. This means the vapor is much better at absorbing the impurity. The second principle is the operation relationships, which looks at the flow rate of the two phases. Here, for every kilogram of the cream that phase through the system, 0.75 kilograms of the vapor are used. These two principal equilibrium of the rate are essential to calculate how much impurity remains at the end of the process. The process starts with contaminated cream that has an initial concentration of the 8 ppm of impurity. This cream is then brought into contact with pure vapor, which contaminates no impurity. During this interaction, the impurity transfers from the cream to the vapor. To calculate how much impurity is left in the cream after no stage, we use the formula that combines the equilibrium and the flow rate relationship. The formula is X1 is the initial concentration in the cream, and X0 is the initial concentration. And the use L by V is the ratio of the liquid to the vapor flow, and the K is the constant that describes the equilibrium. In this case, K is equal to 10. When we apply this formula with the example data, we find that the impurity concentration in the cream is reduced from 8 ppm to about the 0.9 and 49 ppm after use 1 day stage. This shows how effective the process is at removing impurities. For example, in this case, this technique is very useful for the purifying the materials and industries because it allows you to the precise control and reduce wet components. Using this equilibrium and the flow relationship ensure the process is both efficient and optimized.